All right, everyone, welcome back. So we're taking a look at 8.2 today, the ellipse, ellipse shape. So the ellipse is going to look like a circle, but it's been kind of like squished or elongated horizontally or vertically. And you can see there's a bunch more information going on here. We have what's called vertices and co-vertices. The center, obviously, things called the major and minor axis that are connecting the vertices are the co-vertices. And what's also called the foci for these shapes. Those are the points that say F. Right about here and here. And you have these different distances, A, B, and C, throughout this. So there are going to be different relationships to create with that. So the technical definition, ellipse is a set of all points in a plane such that the sum of the distances from the two fixed points is constant, and these points are called foci. Every ellipse has two axes of symmetry, the major and minor axis, perpendicular at the center of the ellipse. The major axis, as the name suggests, is the longer of the two. The minor axis is the shorter of the two. The foci always lie on the major axis. They lie inside the shape. The endpoints of the major axis are called the vertices, whereas the endpoints of the minor axis are called the co-vertices. As for your equations, whether it's going to be horizontal or vertical, again, elongated horizontally or elongating vertically, it'll be this format right here. It's always going to be x minus h squared and y minus k squared as fractions adding together to equal 1. The question is where a versus b is going to go, because a is always bigger than b, because a is part of the major axis and b is part of the minor axis. And then how we find the foci, vertices, and co-vertices is taking the center at hk and either adding or subtracting a, b, or c. The foci add and subtracts the value of c. That's a distance away from the center of the foci is. The vertices is the value of a, and the co-vertices is the value of b. And you'll see that for the horizontal ellipse, the foci and the vertices are adding and subtracting a and c to the x-coordinates, whereas the co-vertice adds and subtracts b to the y-coordinates. And then for vertical, it's switched. The vertices and foci adds a and c to the y-coordinate there, and then co-vertice adds it to the x-coordinates. So if they give you, the way we're going to be able to tell if something is horizontal versus vertical, we'll be able to look at the vertices and see, okay, what value is changing? The value that's changing, if x is changing, it's horizontal. If y is changing, then it's vertical. And then a, b, and c all have a relationship that's based on the Pythagorean theorem. It's not your traditional a squared plus b squared equals c squared. It still technically is, but the letters are switched around for this particular problem. It's b squared plus c squared equals a squared. And typically we're going to use this to solve for either b or c. So like c squared, for example, is a squared minus b squared, or b squared is a squared minus c squared. All right, so let's jump into this. So writing the equation, you're going to need to know what the center is and the values of a and b. And then also figure out whether it's horizontal or vertical, because if it's horizontal, a is the bigger value and it's going underneath the x's, whereas if it's vertical, a is still the bigger value, but now it's going underneath the y's. So if we're given the vertices and the co-vertices, we can find a and b directly once we figure out the center. The center will always be the midpoint of the vertices, the midpoint of the co-vertices, or the midpoint of the foci. So our center, if we do our midpoint for the vertices, 18 plus 0 over 2, 3 plus 3 over 2, we get 18 over 2 and 6 over 2, which is 9, 3. So our center is at 9, 3. So we're going to have our equation be x minus 9 squared, and then y minus 3 squared equal to 1. And we got to fill in where a and b are going to go. Now, if you look at the vertices, the value of x is changing. We went from 18 to 0, whereas the value of y did not change. So because the x's are changing, I know this is horizontal. So because it's horizontal, a squared is going to go underneath the x expression, whereas b squared goes underneath the y expression. And the way we find a and b is very straightforward. A is always the distance the vertice is from the center. So the vertice goes from 18 to 9 to go to the center. So I do 18 minus 9, which means a is 9, so a squared is 81. B is the same idea, but with the co-vertices. So we would say the co-vertice changes from 9 to 3, so it's 9 minus 3, which is 6, so we get 36 for b squared. So our equation, we would put the 81 underneath the x's and the 36 underneath the y's. And there's our equation. All right, so again, center is always the midpoint of the vertice or co-vertices, and then the values of a and b are how far away the vertices and co-vertices are from the center. It's a simple subtraction problem. If you get a negative, it doesn't matter because you're squaring it, so it becomes out to be a positive. The negative would just imply it's on the negative side of the center. So for this one, we can now see that this one's going to be a vertical ellipse because now the y-coordinates are changing. So we have a vertical ellipse. Center is still going to be the average of the x's and y's, so it's -3 plus -3 over 2, 23 plus -3 over 2. Ultimately, we would get for the center -3, 10. Now, you might have noticed in the previous one, you're definitely going to notice right now, if you're given vertices and co-vertices, you can actually avoid doing the midpoint formula because the unchanging value for each of them, -3 for the x's for the vertices, and then 10 for the co-vertices, would represent the coordinate point of the center. That's how it's always going to be if you happen to be given vertices and co-vertices. If you're given vertices and like anything else, you will still have to calculate out the center by doing a quick midpoint formula. But otherwise, that's how that would work out for us. Okay, so we've got our center. We know it's vertical. So we know that a squared is going underneath the y's. So our value of a, again, is how far the center is from the vertice. So it's changing from 23 to 10. So a is 13, so a squared is 169. Whereas b is how the co-vertices change. So I'm going from 1 to -3. So b is 4, meaning b squared is 16. So my equation would say x plus 3 squared over 16, and then y minus 10 squared over 169. Because again, remember, the larger number goes with the appropriate fraction based on the orientation. Because it's vertical, the larger number, the 169, goes with the y fraction. Whereas the smaller number obviously goes in the other spot. All right, so that's your horizontal versus vertical for the vertices and co-vertices. Here we have vertices and foci. So this gives us the same kind of stuff. We can find the value of a from the vertices, we can find the center from the midpoint of the vertices, and we can find the value of c from the foci, and then we'll have to use a and c to find b to figure out the equation of our ellipse. Once again, we notice that the x values are changing, so this is going to be a horizontal ellipse. Our center is still our midpoint of the vertices, so it's 6 plus -4 over 2, -3 plus -3 over 2. So ultimately, we get for the center, we get 1, -3. So we have x minus 1 squared, y plus 3 squared, over some number equal to 1. A is how far the vertex is from the center, so we're changing from 6 to 1. So a is 5, therefore a squared is 25, and because it's horizontal, it goes with the x's. C is the foci, so how far the foci changed from the center, so c would be 5 minus 1, which is 4, so c squared is 16. And again, that's not part of the equation there, but we do use it to solve for b, because if you remember from the first slide, or not the first slide, but one of the beginning slides, b squared plus c squared equals a squared. That was the relationship between a, b, and c, and this is why we need that, because if I have a and c, I got to be able to find b. Or if I had b and c, I got to be able to find a. So we fill in, so b squared plus 16 equals 25, so that means b squared is 9. And there's our answer. And so far, these values have all been perfect squares for the a, b, and c. It doesn't necessarily have to be. A, B, and C could be based off radicals. If we're graphing, it probably won't be, at least for A and B. But for writing the equation, it certainly can be because we're not trying to graph this thing, so they can be whatever numbers we want it to be. All right, so we got vertices and foci here. This one is now clearly going to be vertical because the y values are the ones that are changing here. So this is going to be our vertical ellipse. We recognize that our center is going to be, again, the midpoint of the vertices, as always, -3 plus -3 over 2, and then 20 plus -6 over 2. So we get our center to be at -3, 7. So we would have x plus 3 squared over some unknown, and then y minus 7 squared over, again, some unknown, all equal to 1. As we've always been doing for the previous 3 examples, we're going to continue doing this. A is how far the vertex is from the center. The vertex changes from 20 to 7, so it's 20 minus 7, which is 13. So a squared is 169. And again, it's vertical, so it goes with the y's. The foci is the value of c. It's how far the foci is from the center. So going from 19 to 7, so 19 minus 7 would tell us the foci is 12, so c squared is 144. So then we use our b squared plus c squared equals a squared formula. So b squared plus c squared equals a squared, so b squared is 25. So it'd be a 25 down below the x plus 3. So we're going to stick with only, at least for our purposes, just working with the vertices and covertices, vertices and foci to write out the equation in terms of given coordinate point information. There's a couple other things you could be given, but those are primarily what you're going to be given for that. Because we need to be able to figure out what the center is and then finding the values of A, B, and C and everything else. Now, we could also be given an equation in its general conic section format. This is always like with the circle we saw from 8.1, the x squareds, y squareds, x and y's, and a constant all just kind of foiled out and grouped together on one side. So the idea is you're going to group the x's together, group the y's together, and complete the square to write your equation. So completing the square requires to take a 3 away from the x squared and the x, and it requires to take a 4 away from the y squared and the y. And then we move the 17 over to the opposite side. It always has to be like that. There is no choice in terms of if there happens to be no number in front of these square terms, you obviously don't have to factor that out, but you are going to always need to factor that number out. Completing the square does not work correctly otherwise. Filling in the blanks, again, it's half the middle number divided by 2. Half the middle number squared, not divided by 2 again. So half of -6 is -3, squared is 9. To balance, it needs to be 3 times 9 on the right side. Because it's not just simply a 9 we're adding on the left, it's 3 times 9 because the 3 factored away. Same logic for the y part. Half of 14 is 7, 7 squared is 49. It's got to be a 4 times of 49, balancing on the right-hand side. Simply because, again, it's not just 49 we're adding in, it's a positive 4 on the outside as well, so they're multiplying. So this would give us 3 and then x minus 3 squared, 4 and then y minus 7 squared, equal to, 17 plus 3 times 9, plus the 4 times the 49 gives us 240. So the proper format was all fractions equal to 1, so we're always going to divide by whatever we get on the right-hand side, in this case 240. And we get x minus 3 squared over 80 plus y minus 7 squared over 60 equal to 1. And there's now our proper standard form equation of the ellipse. All right, so one more with that. So we can see we're factoring the 4 away from the x squared and the 72, grouping that together. And there's nothing to factor away from the y term, so we can just kind of leave that alone, the y squared there. And we're subtracting over the 225 over to the right-hand side. So filling in that blank, half of 18 is 9, 9 squared is 81. So we're balancing with the 4 times 81. And then there with the y's, half of -2 is 1, 1 squared is 1. So we're just adding a 1 in on the right side to balance that out. We get 4 times x minus 9 squared, y minus 1 squared, and then we do our -225 plus our 4 times 81 plus 1, we get 100. And then we divide everything by that 100 because it always has to be fractions adding together to equal 1. And we get x minus 9 squared over 25, and then y minus 1 squared over 100 equal to 1. So that's our writing of the standard form equation of the ellipse based on either giving us coordinate point information, vertices and covertices, vertices and foci, or just the standard equation. We also have the graphing. So graphing will need to identify center, vertices, and covertices. You also will need to identify the foci as well. I'm going to ask for that as part of what you should be looking for in the equation, but you're not going to plot that because it's inside the shape. It's not going to help create the shape in terms of what you're doing. Technically, they're what actually create the shape because they're the equidistances portion there, but that's not really how you're going to ever graph. So we're given the information so we can tell that h is going to be 2, k is going to be -1, a squared is the bigger number, 36, meaning a is 6. B squared is a smaller number, 25, which means b is 5. And then again, we have our b squared plus c squared equal to a squared. So therefore, 25 plus c squared is equal to 36. C squared is 11. Therefore, C is going to be square root of 11. Now, all of that's going to be put together to figure out our center, vertices, co-vertices, and the foci. So our center is just simply H and K. So it'd be 2, -1. Our vertices, well, we need to figure out whether it's horizontal or vertical, because we need to know whether or not I'm adding A to the X's or adding and subtracting A to the Y's. Well, the larger number, 36, is underneath the X expression, so this thing is going to be horizontal. So I'm going to add and subtract A to the X coordinate points. Doing so gives me 8, -1, and -4, -1, which means the co-vertices, I'm going to add and subtract B to the Y coordinate, then the opposites. So it's 2, -1 plus or minus 5, giving us 2, 4, and 2, -6. And then the foci, we're going to add and subtract C to the X coordinate because it's the same as the vertice adding to the X because it's horizontal. 2 plus or minus root 11, -1. You can separate that out into its 2 actual coordinate points there. So you can say that would be 2 plus root 11 minus -1 and 2 minus root 11, -1. Because you can't actually combine them, you're also welcome to just leave in the plus or minus formats, similar to what we would do if you had something like the quadratic formula, for example, where you would have the plus or minus in there. You kind of like group the answer like that. Obviously, if C was an integer, then you can give me 2 actual coordinate point answers there. But a lot of times you'll find C would be a radical for these graphs, so you just kind of, that's another reason why we don't worry about plotting them. All right, so now we have everything we need to plot the graph out. So we go ahead and plot our center first, 2, -1. And we plot our vertices at 8, -1, and -4, -1. I'm going to label them V1 and V2, where I'm going to go left to right. So the left side is V1, right side is V2. Doesn't really matter. Plotting the co-vertices at 2, 4, and then 2, -6. Again, it doesn't really matter which one you're calling, CV1, CV2, just make sure you label them as the vertices and co-vertices. And then kind of like the circle, you're just kind of connecting them. Make it look like a curved shape as best you possibly can. Not too bad. You'll find that it's more circular in nature the closer in value the A and B values are going to be, because this is telling us it is elongated horizontally, but by only a little bit versus the vertical. If A was like 9 and B was like 2, that'd be a much more drastic change, so there'd be a much more elongated shape in that case. But the closer they are together, the more circular they are. All right, so that was a horizontal ellipse. Let's talk about a vertical one. Same process and all, but just kind of you'll see it's a different shape. And again, you can recognize this one as vertical because the larger value is part of the y fraction. The 25 is part of that. So we go ahead and find our h and k. H is -3, k is +2. It's always the opposite of inside the expressions there. A squared is the bigger number, which is 25, which means A is 5. B squared is a smaller number, which is 16, so B is going to be 4. And then your C squared again is B squared plus C squared equal to A squared. So C squared is 9. So in this case, C is a nice number, C is 3. So we will be able to get actual integer values for the coordinate points of the foci. But if it's not, then again, you always just leave it in that radical format there. So our center is always h comma k, so -3 comma 2. Our vertices, because it's vertical now, I'm adding and subtracting a to the y coordinates. So it's -3 and then 2 plus or minus 5. That gives us -3, 7, and -3, -3. Whereas the co-vertices are now going to abstract b with the x coordinate, the opposite of the vertices. So it's -3 plus or minus 4 comma 2, getting us 1, 2, and -7, 2. And then our foci, we're going to abstract the value of c to the y coordinate, because again, it's vertical, so it does the same thing as the vertices. Foci always does the same thing as the vertices. So -3 and 2 plus or minus 3. We get -3 comma 5 and -3 comma -1. Again, you don't need to actually plot the foci. It's not part of what will create the shape while you're doing it by hand. It's technically what creates a shape mathematically, but for the actual graphing purposes, you're going to leave that part alone. So we go ahead, we plot out our center, -3, 2. Vertices at -3, 7, and -3, -3. If we just want to call them V and V, so you're not really doing V1 and V2, that's perfectly fine. And our covertices at 1, 2, and negative 7, 2, so we can just call them CVs. That's perfectly fine. Again, we just kind of connect them. Make it look like it's kind of circular in nature. I kind of got a little mess up there in the right quadrant, but it's perfect. It's fine. I'm not looking for perfection with these things. Don't stress over that. All right, so that's our ellipses. Writing the equations, graphing the equations. That's what we're looking to do for each of these shapes. So next up is the hyperbola, which will be similar format in terms of the equation setup that was the ellipse, but there's going to be some key differences, obviously, because it's a different shape. And then the parabola next, which you'll recognize from quadratics, but there's a couple of key differences we'll talk about with that one. All right, so I'll see everyone next time.